All right, this is a overview of the atomic nature of matter assignment, and the idea you kind of can see here in this little demo. You've got you can imagine this blue ball here is like a polystyrene bead in some water, and the little red guys are little atoms that keep bouncing into it and making it move around. And it turns out if you can track the motion of this bead in the water, you can recover some physical constants like Avogadro's number. And this assignment, you're going to develop a number of different programs, and those programs in cooperation are going to be able to compute those physical constants. Okay, and you can read a little bit about the history here and so on. And don't get too freaked out. You don't have to be, I'm not a physicist either. You don't have to understand a lot of the physics in order to do this assignment. You just have to understand sort of the process you need to go through and the software you need to build in order to do the assignment. And it starts off with this zip file. Okay, so you should download that, and probably I think you need to copy some of the support classes from Princeton. Like you'll need the picture class, and you'll need the luminance class, and you'll need stopwatch class, and maybe a few other things. But what the zip does have is all these images, and so somebody videoed. Let me pull up the video first. Where is my? Oops, I think I closed my video. Okay, I have to go find the video again here. Hold on a sec. Okay, so here's the video. Okay, and this is kind of the source where all these JPEG images are just frames in this video. So this is a video of those little polystyrene beads bobbing around in some liquid, and you can see the little haloed ones are ones that are just out of focus, out of the focus plane of the camera being used. But the idea is we're going to write a program that's going to track the motion of those little white ones that are well defined. Okay, and so let me go back to my workspace here. Okay, each of these run directories, right, is just a bunch of JPEGs that are 640 by 480, and you kind of flip through them, and you can kind of see, you can kind of see the video going there. Okay, you're just going to operate on the still frames in this assignment. All right, and so I've got some slides I can show you from Princeton about the assignment, and so why don't we go through there. The basic goal is to estimate that Avogadro's number in using some equations and so on, and we're going to use this fluorescent imaging of these beads in the water to do it. Okay, your input data is going to be this sequence. So one of these runs has, I don't know, several hundred images in it. It's a sequence of images, so they're numbered, in time sequence, and each is a rectangular set of pixels, 640 by 480, and we're going to make a threshold decision. Either a pixel is light or it's dark. Okay, and we'll talk about the details of that, and then based on that we'll estimate the physical constant. You're going to be developing 4 different programs to do this. Okay, and probably this is the order you should work on them in, though you can do, if you want to do Avogadro with one of our input files, you could do that without having done the rest of them, but most people just do it in order. And the first one's a fairly simple data type called a blob, and a blob is going to represent what we think is potentially a bead, a collection of pixels that are white. Blob finder is going to be sort of the workhorse. It's going to look at an entire picture and find all the blobs that are in it. It's going to find things that it thinks are these beads, and that's kind of where the hardest part is. The smarts of the algorithm are in blob finder. Okay, once you know where the blobs are, and then the other kind of smart bit is the bead tracker. And so bead tracker is going to do is take 2 frames in sequence and try and figure out where these blobs that blob finder found, how far did they move between one frame and the next. And then finally the output of the bead tracker program is going to be the input to the Avogadro program, and then that's going to do some of the physics equations. All right, it's all about Brownian motion. So you've got your bead is the kind of the green thing, and it's getting hit by the little atoms and so on. And this displacement fits a Gaussian distribution. And what we eventually get out is this number, right? It's going to be, somewhere near 6.02 times 10 to the 23rd. That's the number of atoms you'd need to equal the atomic mass of a certain particular element. All right. But like I said, the physics aren't, you don't have to really understand all the physics to do this assignment. Okay, so don't worry about it if you're not that up on your physics. All right, let's start talking about blob. Blob's the first thing you have to implement. Okay, here's the public API for blob. It has a constructor. You can add a pixel to it. You can figure out its mass, and so the mass is just how many pixels are in the blob. You can calculate the distance from yourself. You're a blob. What's the distance to some other blob? All right, and we're going to use the center of mass of the blob to determine that distance, and then we can print some stuff out about it in toString. All right. Note this final bullet here, okay? While the blob data type could be responsible for actually tracking all the pixel values, say you actually wanted to draw the blob on the screen or do something more sophisticated, you would need to store all these pixel locations. But our blob is just there to support the calculations. It doesn't really need to know anything more than its center of mass, and so it's x and y of its center of mass and the total mass, how many pixels have been added to it. So you can do it with just 3 values, okay? Don't do anything more sophisticated than that, like storing all the pixels. That's not really necessary. Some challenges in the blob data type. You want to format your numbers in a nice way, and so you should know by now how to use the printf or the string format function. Those will be your friends here, and you can use that to get things either with a certain number of decimal places, or if you use the %e, you can get things in scientific notation. All right. Make sure your blob's are working before you go on. Create a simple test main and make sure everything's going as expected with the blob. All right. If your blob doesn't work, nothing after that in the chain is going to be too successful. Blob Finder. So Blob Finder loads in a picture. You can see its constructor here. It takes a picture in, okay, and then it also takes a tau, and tau is our threshold value on the luminance. And if you've got what luminance is, you can go look in the Luminance Java or 3.1. Okay, you can just use this class. You don't have to do your own luminance calculation. There's a static method in this class you can use, and you can give it a color object and it will return luminance. Pixels are considered white or light if their luminance is greater than or equal to whatever this tau threshold is. Okay, and we'll look at this on the next slide, but we're going to use a depth first search. So this is similar to the percolation example in the textbook in 2.4. This is kind of the trickiest part, and I'll show you a diagram on the next slide about that. And once your blob finder has found the blobs in its constructor, then it stores them off somewhere. So you have some data structure holding all your blobs, and then it can tell you how many things are in it. Okay. Oh yeah, I forgot to say there's a difference between a bead and a blob. Okay. All right. Blobs are just some connected set of pixels that are greater than or equal to the tau value. If a collection, if one of those blobs has more than a certain, has at least p pixels, then we're going to call it a bead. All right, and a bead is, one of those polystyrene thing that's bobbing around. Okay, and we're going to have some threshold like 25. You need at least 25 white pixels in order to count as a bead. Otherwise, maybe you're just noise in the video. All right, so that's the difference between a bead and a blob. You always have, usually have fewer beads than you have blobs in your blob finder. All right, and finally you've got given that threshold, you can get just the array of blob objects that are in fact beads. Here is a diagram of how the depth first search should work in Blob Finder. The idea is you're going to set up a Boolean array that's the size of the number of pixels, okay? And you can start, all the values, start off as false or something like that. And what you're going to do is you're going to traverse through this 2D array of Booleans and mark things, okay? And if you encounter a pixel value and you just discover it's dark, so here we're kind of imagining the red is light pixels and the white is dark pixels, say. Okay, so it's kind of backwards, but never mind. Say this is black up here, so you go to that pixel, realize it's the dark pixel, you just mark that in the Boolean array as visited, okay, and move on to the next one, and same there, and then same there. Okay, it gets interesting once we're down to this red one. So this passes our luminance greater than or equal to tau test, therefore it's a light pixel, okay, and it's going to result in a new blob being created. All right, because it wasn't marked already. We have a new blob, we create a new blob object, and then what we're going to do is try and find all these other red guys and add them to that same blob object. All right, and this is very easy to do if you do it with a recursive algorithm, and like any recursive algorithm, it needs to have its base cases. All right, and it's going to need to make sure it doesn't go out of bounds in the 2D array. It needs to make sure it doesn't redo work, so if it doesn't want to handle these pixels up here already because they've already been handled once. All right, and if it comes down here, it doesn't want to start adding pixels that are dark, that aren't passing the threshold test. All right, its recursion is going to be in 4 directions: straight north, straight south, straight west, and straight east. Don't go on the diagonals, okay? Just in the 4 cardinal directions. And here's it graphically. Okay, I think, oops, hold on, what's going on here? Okay, there we go. So we found that red one, right? We marked it, added it to the blob. Then we went left, and then we went, oh well, we better not do anything there, we're out of bounds. So that's a base case. We don't recur on that call. All right, so we drop back to the caller, and then they recur on the north. We realize the north has already been marked, so we base case out of that. Then we go south. Well, south doesn't pass the threshold test, so we base case out. Okay, but we go to the right, and right we go, oh, actually this pixel does pass the test, and it hasn't been added already. So this second pixel is now going to be added to my blob. All right, and then once that's been done, this guy is going to recur north, south, east, and west, and the process is going to continue. And what's going to happen in the end, after that recursive algorithm finishes, it's going to have marked this pixel and all its connected pixels. These will all be added to the same blob object, and some of these other guys in the 2D Boolean array will have been marked as visited because we tried going further right but failed. All right, then the algorithm is going to carry on. It's going to check this one, it's already marked, this one, it's already marked, this one, it's already marked, and then it'll come down here and realize this one's white, and so on. And it'll just keep doing that all the way through here, and then once it finally gets over here, it's going to add the second blob object. All right, that's the basic procedure. Okay, it's a small amount of code, but it needs to be the right code. You can store your blobs. Okay, you need to store off those blob objects. So in this case, right, we're going to have some data structure in our blob finder holding 2 blobs. We're not going to know in advance how many blobs we're going to find, though. So you need some sort of data structure collection that can hold that. All right. And here are some choices. A straight array, but you don't know how big it's going to be. You could use a linked list. You could use something else that's built into Java, for example, that you learned about in a past lecture. Bead tracker. Okay, thus having found the beads in a particular frame, bead tracker operates on 2 frames. Okay. At some time and then some time plus some delta, it's going to try and figure out what distance these beads move. How far did their center of mass move between time 1 and time 0. All right, and bead tracker is going to have to load each of those frames in sequence and then compare the beads found in time 1 with the ones in time 0, and then output those displacements. All right. And it's arbitrary which direction you do this, but you need to do it the way we said in order to get the same answer. Okay, so just to make your results match, you should compare each bead at time t plus 1. What you do is you look through all the other beads in time t, find whichever one's closest, and then you assume that's your, that's where you used to be. Okay, it's an assumption. It may not always be correct, but it's, it's good enough for government work. Um, there's also some cutoff value. Okay, if you find, the nearest bead is really far away, then maybe that's just a new bead coming into focus on the camera or something like that, and then you don't output the displacement. Bead tracker takes a bunch of command line arguments. It takes the number of pixels required to be considered a bead. It takes the tau, the luminance threshold. It takes the delta, so this is the max distance to be considered, the same bead in the bead tracker. And then it takes, okay, a bunch of JPEG frames. So what actually happens when you do something like this is the Unix form with the /. This is going to get expanded out, and it's actually going to come in the args. All right, we've got args0, args1, args2. The first JPEG is going to be args3, and then args4 up to args 205 or something like that. All right, you're going to get access to these file names just by looping through that args array. All right, and that's just basically what that's saying. Be careful with your bead tracker. Bead tracker, while in principle we could track these beads throughout the entire video, we don't do that. We just look for the displacements between two frames. All right, we're just moving frame 0 and 1, and then we're looking at 1 and 2, and then we're looking at what did I say, 2 and 3, and then 3 and 4, and so on. Okay, you only need to have 2 frames loaded at any one time. Okay, so don't go loading all the frames at once into picture objects, because that'll take a lot of memory. All right, and just be careful if you make any changes. Make sure you recompile everything. Usually, if you're using Eclipse, it's pretty good at it. If you're at the command line, it's not a bad idea just to do Java C star.java just to make sure everything gets compiled. Final program, Avogadro. This is probably the easiest one, other than I'll show you the assignment page. It involves a lot of equations, but they're really, it's not that hard once you figure out exactly, how you're supposed to, add things up and divide them. Okay, it's really not that big of a deal, and you just got to be a little careful. Make sure you convert your units and do things in the right order, get your order of operations right, and if you do all that, it should output the right number. All right, and be careful, how you're passing things around in Blob Finder and so on, and you'll see, various. Be careful if you're getting stack overflows in your Blob Finder. It's probably because you don't have your base cases implemented correctly. If you're getting null pointer exceptions, probably that's often a base case problem in your recursion as well, and so on. All right, and here's the assignment page. Let's see if there's anything else I haven't mentioned that wasn't mentioned in those slides. Okay, you'll find all the details here. You'll find some example runs. Okay, if you run your Blob Finder, once you have Blob and Blob Finder, you can run it on run 1, a single frame, and you should get 13 beads and 15 blobs. All right, and the exact order you're going to get this depends on that data structure you choose. Okay, but if you use the same one we use, then you're going to get it in the same order. Okay. And let's see, particle tracking. Once you get bead tracker working, you can run it on all the stuff in run 1, and then you'll get these displacement values. Okay, if you're not getting the same values, there's probably something wrong. All right, and then finally, these equations tell you how to use those displacements to compute the physical constants. All right, and you got this equation up here, but what you need is this one, which is saying we're taking those displacements and squaring them, adding them all up, and then dividing by 2 times the number of displacements that were in the file. Okay, pretty straightforward. Just be sure you convert your distance in pixels to meters, right? Pixels isn't an SI unit. All right, you need to go to pixels, or you need to go to meters rather. Okay, do that. That gives you, one of the things you need here in order to compute. Let's see, which one's which. And the radius of the bead, I think that was the K, and so basically then you can solve for the unknown, and so on, and then eventually you get down to finding this, and you can find Avogadro's number. Okay, so just read through these. It's not, it's just simple algebra basically. Okay, sum these guys up after you convert the units, divide by 2. Okay, plug in, solve this for the one unknown, and then solve this for the one unknown, and then you'll have your Boltzmann constant and your Avogadro's number. All right. You can check the help here if you're having, any common problems. A lot of the common problems are in here. I would like you to do performance analysis on the bead tracker. All right, the bead tracker is sort of the performance hog. It can take 10, 20, 30 seconds or something to do one of these runs. All right, I'd like you to use the doubling hypothesis to come up with a hypothesis about the order of growth of this algorithm. All right, and doing this involves running the bead tracker on different numbers of frames. Obviously, you want to run it on, like, say 50 frames, and then 100, and then 200, and then 400, and so on. All right, and it's a little easier if you're on Unix or Mac OS. It has better support for wildcards. A little more difficult in Windows, but you can always just make some directories and copy. It doesn't matter so much what the actual frames are, just that it's just the total number. So for example, this run has whatever 200 or however many are in run 1. All right, and you can double it by just doing it twice. Okay, and it's not nothing too wrong with that. You've got a little gap in there, and it's going to calculate stuff, but it doesn't really matter. Okay, that'll effectively double the n size, so you can do something like that. And then I'd like you to include a README file showing me the data you got from your performance analysis, as well as your conclusions about what the exponent is in the order of growth, as well as solving for the constant out front. All right, so I think that's it. Good luck, and let me know if you have any questions.